Welcome to Strength of Material Lectures by Civil Thinking, and today we are going to solve a problem on torsion in shafts, okay, or torque in shafts. Now the problem is on your screen. Given that the allowable shear stress in shaft is 60 megapascal, what is the required diameter of the shaft if it has a solid cross section? And B is what is the required outside diameter of the shaft if the shaft is hollow with an inside diameter of 2.5. Okay, now as you can see the picture on the screen, this is a shaft. Okay, now you can see there is a torque acting at A, B, C, D. Okay, now 8 kilonewton it's acting something like downwards. Okay, at B it is acting like upwards, C downwards, and D downwards, right? Now the part A is we have to find the diameter D. Okay, now the allowable shear stress in the shaft is 60 megapascal. Okay, so whatever the shear stress is here, we know due to these torques there will develop the shear stress in each cross section, right? In each cross section there will act some shear stress. Okay, now whatever is the maximum shear stress, of course at some cross sections the shear stress will be more than others. Okay, but whatever is the maximum shear stress in whole of this shaft, that maximum shear stress should not exceed 60 megapascal, right? Or in other words we can say the maximum shear stress tau has to be equal to 60 megapascal. Okay, now mega means 10 power 6 pascals. Okay, and pascal means newton per meter square. Okay, this is the maximum shear stress. Now what is the required diameter D? Okay, now to find the required diameter D, we have to find an equation of diameter D in terms of the shear stress and these torques. Okay, now we know the torque equation. It is T by J is equal to tau divided by R. Okay, now T, it is the torque. Okay, or maximum torque on the shaft. Now you can see here is 8, 19, 4, 7, which is the maximum. Okay, please keep in mind you cannot say this is the maximum. Okay, because this torque is internal torque and we have to find this maximum torque using some diagram which we called as torque distribution diagram. Okay, anyways, now J is what? J is polar moment of inertia. Okay, polar moment of inertia. Now tau, as we have explained before, tau is maximum shear stress. Okay, which is 60 multiplied by 10 to power 6 newton per meter square. Okay, now R is the radius. Okay, radius of the outer surface. Okay, now you can see the shaft, the outer surface is this, right? This is the radius of outer surface. Okay, the radius will begin from center to outer surface. Okay, this is the radius. What we are going to do, we will first find the radius because we have to find the diameter D. We know the radius is half of the diameter, or or we can also find the equation of diameter. Okay, we will find the equation of diameter D. Okay, now this torque, we will find this torque using torque distribution diagram. Okay, TDD. Okay, now let me draw the torque distribution diagram. Let me draw these lines. They will help me draw the diagram. They will help me. Okay, this is the baseline. Okay, let me extend them to lower points. Okay, this is torque distribution diagram. Okay, before I continue, I want to tell you, you can download the PDF of this video lecture from the link in the description. Okay, but don't worry about writing, just try to understand. and at the end of this video lecture you can download the PDF. So don't write, just understand. Now this is the baseline, zero torque. Okay, now above this baseline, okay, the torque, I will draw the positive torques, and below this baseline, the zero line, I will draw the negative. Okay, now the question is which of these torques is negative and which of them is positive. Okay, for that I have to make assumption. Okay, let me assume these downward torques like 8, 4 and 7. Let me assume the downward torques as negative. Okay, the downward torques I will assume as negative, and upward is only one at B, the 19 kilonewton meter. Okay, upward I will assume to be positive. Okay, so let me begin from left to right. Okay, this is the assumption for left to right. Okay, now at A there is an 8 kilonewton meter of torque, right? But it is downwards, means negative. Negative is below the baseline, so I will draw a line. Let me say this is 8 kilonewton. Okay, now from A to B there is nothing, no torque, so I will go flat here. You can understand this is point A, B, and this is C, this is D, right? Because as you can see, now at B there is an upward torque of 19. Okay, so I have to go up by 19. So let me go first up by 8, because I know from here to here is 8. Then what is remaining? Now I have to go more 11. Okay, because 11 plus 8 is 19. Let me assume this to be 11. Okay, now from B to C there is nothing. Now at point C there is a downward movement of 4. Okay, so I will go 4 down, right? Now from here to here is 11, right? Because this is 11. So how much is this? From here to here I went 4 down, right? I went 4 down, so 11 minus 4 is 7, right? This is 7. Now from C to D there is no torque, so I will go flat, right? At D there is downward of 7. Okay, now from here to here is 7, so I will go 7 downwards. Okay, now from the torque distribution diagram, as you can see here, you can see the torque in AB. This is AB, right? This is the torque diagram for AB, right? Now what is the height or depth of torque diagram of AB? It is 8. It means torque in AB, okay, it is 8. Now in BC, this is the diagram, right? All of this. What is the height or depth of this BC? It is 11. It means torque in BC is 11. What 11 what? Kilonewton meter, right? Kilonewton meter, keep in mind. Now this is CD, right? Now torque in CD is what? What is the depth of this diagram? It is 7, right? So it is 7 kilonewton meter, right? Now in AB is 8, BC is 11, and CD is 7. Now you can realize that it is all the way different from these torques, right? Here is no, you can see here is no 11. Okay, first if we will see in this diagram, we can wrongly interpret the torque, maximum torque, to be 90, right? Because it seems to be maximum all of these, but when we see the torque diagram, we found that the maximum is which one? 7, 11 or 8. The maximum is BC. Okay, it means torque, okay, it is 11 kilonewton. Okay, or I can write it as 11 kilo means 10 to power 3, right? So I can write 000 Newton meter, right? So from here we get the torque. How much? Torque is 11,000 Newton meter, right? Now J. Now J is polar moment of inertia, okay? Polar moment of inertia of the cross section, okay? Of cross section. Now you can see this shaft have a circular cross section, okay? Like this, as you can see here, okay? Let its radius be R, okay? Let me consider two axes. One axis be here, another axis be here. This is x axis, this is y axis, and this is z axis, right? Now we know the moment of inertia of a circle about x axis, okay? Ixx is pi r power 4 divided by 4. Also moment of inertia of this circle about y axis, because it is symmetric, right? So moment of inertia about x axis is same as moment of inertia about y axis, right? So it is also equal to Iyy. Now z axis is perpendicular or normal to the surface, right? And the moment of inertia about this normal z axis, which is normal to this plane, that is known as polar moment of inertia. That is Izz. This is denoted with J, okay? The J you see here, this J or this J, okay? This is moment of inertia about the Z axis, okay? And according to the theorem of perpendicular axes, J or Izz is Ixx plus Iyy, okay? This is according to the theorem of perpendicular axes. Now, if you don't know much about the moment of inertia, all of these Ixx, Iyy, or polar moment of inertia, please watch my video lecture on the moment of inertia. Okay, you will understand it very well. Now, Ixx is pi r 4 by 4, and Iy Iyy is pi r 4 by 4. Okay, now when we add these, pi r4 divided by 4 plus pi r4 divided by 4, right? Ixx plus Iyy. Now when you add up these, they are similar terms, so it is going to be 2 times pi r4 divided by 4, okay? Now here it is 2 ones and 2 twos, so polar moment of inertia is pi r4 divided by 2, right? Now this is pi r4 divided by 2. Now as you can see, r is the radius and tau is the maximum shear stress. Now we have to find the diameter, right? As you can see here, I have to find the diameter. What is the required diameter d? Okay, so I have to convert this equation such a way I have to find the diameter term, okay? From this, then I will find the diameter, okay? So let me erase this first. Now from here we can rearrange this like T is the torque and J is pi r4 by 4, pi r4 divided by 2, okay? Now so I can write T divided by pi r4 divided by 2, right, is equal to tau divided by r, tau divided by r, right? Now it is r4 and this is r, okay? So this r and here will be only 3, okay? They will cancel out, and this 4 will convert into 3, right? And this is tau here, right? Now 2 will go up like this. Now r cube will go here, so what we find, r cube to be 2t divided by pi tau, right? R cube, if we take it to this side, r cube, it is going to be 2t by pi tau, right? Now radius, what is the relation between diameter and radius? If this is a circle, this is the diameter, right? And this is the radius. We know diameter is 2 times radius, or radius is half of diameter, right? So here I can write half of diameter, so d by 2 power 3, it is going to be t 2t divided by pi tau, right? Now it is d cube divided by 2 power 3 is 2, 2 is 4, 2 is 8, is 2t by pi tau, right? It is tau. Now I will take 8 on this side, it is 8 multiplied by 2, which is 16. So we get d cube is 16t divided by pi tau, right? This is the equation. We are going to use this equation, okay? Now d cube is equal to 16 times t, right? T is the torque, which is 1100, 11,000, not 100, divided by pi. Pi is 3.14, and tau. How much is tau? Where is tau? It is 60 multiplied by 10 to the power 6. Now you can, this is d cube, right? This is the value of d cube. Now you can use the calculator and you will find the value of d to be, okay, 9.7 centimeter, okay? So we found the diameter. So this diameter d is what? 9.7 centimeter, okay? Now we have another question. What is the required outside diameter of the shaft if the shaft is hollow with an inside diameter of 2.5 centimeter? Now we have to assume this shaft to be hollow, okay, like this. This is a hollow shaft, okay? It is hollow. It has an inside diameter of 2.5 centimeter, okay? Let me show like this. Let me say this is a cross section of the hollow shaft, okay? And it is like this, okay? Now this is the inside diameter. Let me write it as gi, I for inside, and this is outside, do, okay? Now di is equal to 2.5 centimeter, right? Which is equal to 0.025 meters, right? So this is di, I will write it here, 0.025 meters, okay? We have to find d naught, or outside diameter. Now for a hollow shaft the equation is same like this, but here the r is what? R is the outside radius, okay? This radius outside. Let me change the color. From here to here it is r naught, okay? This is r naught, okay? The polar moment of inertia of a hollow cross section is pi by 2 r outside 4 minus r inside 4, okay? Means outside radius, okay, minus inside radius. This is inside radius, okay, their power 4 minus inside radius power 4 multiplied by pi by 2, okay? And as we found before, tau is same, 60 multiplied by 10 to the power 6, okay? Now just this is a difference, the polar moment of inertia is different, okay, because it is a hollow. Now if you want to know about this, why it is like this, okay, now let me tell you one thing, okay? Now let me draw it again here. This is r outside, this is r inside, okay? Now the moment of inertia of this outside circle, okay, it is what, pi r naught 4 divided by 2, right? As we found before, the moment of inertia, the polar moment of inertia of the outside, it is pi r naught 4 divided by 2, right? Now what is the moment of inertia of the inside circle? It is pi r inside 4 divided by 2, right? Now because the polar moment of inertia of outside and the inside, okay, the inside and the outside, it is about the same z-axis. Remember, about the z-axis is the polar moment of inertia. Because it is about the same, now the moment of inertia, the net moment of inertia of the whole hollow section, okay, it is pi r naught 4 divided by 2 plus pi r inside 4 divided by 2, okay, this is the net, because it is about the same axis. If it was not about the same axis, there would have been no addition, okay. Now since, if you look at this, the outside, this is solid part, okay, it is plus. Now this is inside, it is hollow, right? Here is nothing. This is why here is a negative sign, okay. This is the reason, when you, now here is pi by 2, here is pi by 2, when you put it common, okay, now here is r naught 4 minus ri 4, okay, this is what you get, right, from here. This is the reason I wrote this. Now again, this is not the moment of inertia class, this is a torque class, torque on the shafts. And if you want to know more about the moment of inertia, if you want to know the details about moment of inertia, you can watch my video lecture. Now let me erase this first. Now let me put the values in this equation. So T is what, how much, 11,000 divided by J is how much, pi divided by 2, r naught 4 minus ri 4, right, is equal tau, tau is 60 multiplied by 10 to the power 6 divided by r naught, right? Now when you solve this equation using the calculator, okay, you will get the value of r outside, radius outside, to be approximately 5 centimeters, okay. Now we know diameter d naught, we have to find the diameter, right? What is the required outside diameter? It is d naught, right? We have to find the d naught, and we know diameter is 2 times the radius, right? The outside radius. Now the radius is 5 centimeters, so it is 2 multiplied by 5 centimeter, it is 10 centimeter. So here you go, you found the outside diameter of this shaft to be 10 centimeter, right? In this way we solved this problem, torsion or torque problem in the shafts, okay. So I think that's it for today's class. Now if you need help in any strength or material problems, please contact me. The link to contact me or ask me any numerical problem is in the description. You can ask me there. And I think that's it for today. See you in the next class. Thank you.